In this episode, we are going to treat container isolation as a practical safety problem rather than an abstract security slogan. Because the way you run a container often matters more than the fact that you used a container at all. Containers can make deployment neat and repeatable, but they do not automatically guarantee strong separation between workloads. And attackers know that weak runtime settings can turn a small foothold into broader control. The goal of isolation is to make sure that if one container is compromised, the damage stays contained, the attacker struggles to escape, and other workloads remain protected. Beginners sometimes assume that containers are like sealed boxes by default, yet in real environments the box can have too many openings if you grant too much privilege or share too many resources. By the end, you should be able to explain what least privilege means at runtime, why boundaries matter, and how strong controls keep container compromises from becoming platform compromises. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful starting point is recognizing that a container is not a full virtual machine, and that difference is exactly why boundary controls deserve careful attention. A container typically shares the underlying host kernel with other containers, which makes containers efficient. But it also means isolation is a design you enforce rather than a guarantee you inherit. The container boundary is created by a set of operating system features that limit what processes can see and do, such as file system views, process visibility, and resource limits. When those limits are configured tightly, a compromised container behaves like a trapped room where the attacker can cause trouble inside, but struggles to reach the hallway. When those limits are loose, the container can become a convenient stepping stone to other containers or even the host environment. Understanding that shared kernel reality helps beginners see why least privilege and strong boundary controls are not optional hardening steps, but foundational requirements for safe container operation. Least privilege at runtime means the container gets only the capabilities it needs to perform its intended job and nothing extra that would make an attacker's life easier. This includes privileges inside the container, such as whether processes run as an administrator-like user, and privileges granted by the host, such as special capabilities that allow deep system actions. Beginners often hear least privilege in the context of user accounts, but runtime least privilege is broader because it includes permissions, device access, networking freedom, and the ability to modify the file system in ways that persist. A container that runs as a high-privilege user can write freely to sensitive paths and can access host devices is much easier to weaponize. In contrast, a container that runs as a non-privileged user, has a constrained file system, and lacks dangerous capabilities forces the attacker into a narrower set of moves. The most important mindset shift is realizing that convenience defaults often grant more privilege than a workload truly needs, and attackers profit from that extra headroom. One of the most common beginner misconceptions is that the application inside the container is the only thing you need to protect, as if the container boundary itself cannot be weakened by configuration choices. In practice, the container boundary is strongest when you assume the application might fail and you plan for containment anyway. If your application has a vulnerability and an attacker reaches code execution, your runtime settings determine whether that execution stays limited or becomes a launchpad. For example, when a container has broad privileges, an attacker may be able to change network settings, inspect other processes, or interact with host-level resources in ways that were never intended. Even if those actions are not always successful, the attempt itself creates risk and complexity during response. A well-isolated container environment accepts that exploitation attempts happen and focuses on making post-exploitation progress difficult. That is why runtime isolation is not just a defensive luxury. It is a practical way to reduce blast radius when prevention is not perfect. File system controls are a major part of container isolation because writing to disk is one of the easiest ways for attackers to establish persistence and to stage tools. When a container can write anywhere, an attacker can drop scripts, modify configuration, or place binaries that survive until the container is rebuilt or restarted. Strong boundary controls limit what parts of the file system are writable and, when possible, Keep the container's root file system read-only so that the running workload is harder to modify. This does not mean the application cannot store data at all, because applications often need scratch space. But it does mean that writable areas should be limited, intentional, and monitored. Beginners sometimes think read-only file systems are extreme, but many workloads only need a small writable area for temporary files, and restricting the rest reduces risk dramatically. A constrained file system also improves investigation clarity, because unexpected writes become more suspicious when writing is rare and tightly scoped. Process and system visibility controls matter as well, because attackers often rely on learning what else is running and how the environment is configured. If a container can see host processes or inspect system-level information broadly, the attacker can gather intelligence that helps them escape the container boundary or target other workloads. Strong isolation reduces the container's view of the host and other containers, limiting what can be discovered from inside a compromised workload. This includes restricting access to sensitive system interfaces and avoiding configurations that expose host details unnecessarily. Beginners sometimes assume that visibility is harmless because the container is supposed to be isolated anyway, but information leakage is a classic ingredient in successful attacks. The less an attacker can learn from inside the container, the fewer tailored strategies they can apply. Limiting visibility is therefore a quiet but powerful form of defense, because it forces attackers into more generic, riskier moves that are easier to detect. Network boundary controls are another core piece of isolation, because lateral movement in container environments often begins with simple service-to-service access that was never intended. Containers are frequently deployed in clusters where internal communication is easy, and that ease can turn into overtrust if every container can talk to every other container by default. Strong boundaries define which services should communicate, on which ports, and in which directions, so that a compromised container cannot freely probe and connect across the environment. This concept connects directly to earlier discussions about network flows and unusual access paths, because clear boundaries create clear baselines. When boundaries are strong, unexpected internal connections become high-signal events rather than background noise. Beginners sometimes think internal traffic is inherently safe because it is not public, but internal networks are exactly where attackers try to move once they gain any foothold. So internal segmentation and explicit allow rules matter deeply. Least privilege also applies to what the container can access outside itself, especially in terms of credentials, service identities, and cloud permissions. A container often needs to call other services, and those calls are frequently authenticated using tokens or roles that grant access beyond the container. If those permissions are broad, an attacker who compromises the container inherits that broad access, which can make data theft or infrastructure manipulation much easier. Strong boundary controls, therefore, include scoping the container's external permissions to the minimum necessary and ensuring that secrets are not exposed widely inside the container environment. This is a place where beginners sometimes overcorrect by trying to hide secrets inside images, which is risky because images spread. A better model is to provide access in a controlled way at runtime and to limit which processes can use that access. When a container's external permissions are narrow, the container becomes less valuable to compromise, and the attacker's path to high-value targets becomes steeper. Resource controls are an often overlooked part of isolation, yet they matter because an attacker can cause damage without stealing data simply by exhausting resources. Containers share host resources, and if one container can consume excessive CPU, memory, or disk I/O, it can degrade other workloads and create a denial-of-service effect. Strong boundary controls set reasonable resource limits so that a compromised container cannot monopolize the host or starve neighboring services. This is not only about malicious behavior, because bugs and runaway processes can create similar symptoms, and the same controls improve overall stability. Beginners sometimes think resource limits are performance tuning rather than security, but resilience is part of security, and preventing one workload from harming others is a security outcome. Resource isolation also improves detection, because unusual spikes become more meaningful when limits make normal usage patterns clearer. When resource boundaries are enforced, the environment becomes more predictable, which makes abnormal behavior easier to spot and contain. Host-level exposure is another area where runtime settings can quietly undermine isolation, especially when containers are granted access to host devices or privileged modes. Giving a container deep access to host interfaces can be necessary for certain specialized workloads, but it should be treated as high risk because it weakens the boundary by design. Beginners sometimes grant elevated access during troubleshooting and then forget to revert it, which creates a long-lived weakness that attackers can exploit later. A safer approach is to treat elevated access as a rare exception with strict justification, tight scope, and clear visibility, because the trade-off is significant. When containers run with minimal host access, a compromise remains closer to the container boundary rather than becoming a host compromise. That distinction matters because if the host is compromised, every container on that host becomes suspect, and containment becomes much harder. Strong boundary controls also depend on keeping the runtime environment consistent, because inconsistency creates gaps and surprises. If some containers run with strict settings and others run with permissive settings, attackers will naturally target the permissive ones, and defenders will struggle to maintain a coherent baseline. Consistency does not mean every container uses identical settings, because workloads vary, but it does mean there are well-defined profiles that match workload types and risk levels. Beginners often see runtime settings as a per-container tweak, but mature practice treats them as part of a standard deployment pattern that is repeatable and auditable. This is where earlier ideas about baselines and posture checks fit naturally, because you can validate that runtime isolation settings remain aligned with approved profiles. When validation is continuous, drift in runtime privilege becomes visible quickly, and the window of exposure shrinks. Isolation also benefits from thinking in terms of failure modes, because the moment you need isolation most is when something has already gone wrong. If a container is compromised, you want the attacker's first moves to be frustrating, such as being unable to write to sensitive paths, unable to spawn unusual processes, and unable to reach high-value internal services. You also want your monitoring to pick up on the attempted moves, because blocked actions and unusual connections provide strong signals. This is why isolation is not only about prevention, but also about creating clean, meaningful telemetry that supports detection and investigation. Beginners sometimes imagine that security controls should be invisible when things are normal, yet loud when things are abnormal, and strong boundaries help you get closer to that ideal. When normal behavior is narrowly defined, abnormal behavior stands out clearly, and response becomes faster because there is less ambiguity about what should not be happening. A subtle but important aspect of container isolation is understanding that attackers often look for the path of least resistance, which means they will chain small weaknesses together. A container that runs as a powerful user might not be enough to escape, but if it also has writable access to sensitive locations and broad network reach, the attacker's chances improve dramatically. Conversely, if you apply multiple small constraints, each one reduces the attacker's options, and the combination becomes strong even if no single control is perfect. This layered constraint approach mirrors how we think about cloud security more broadly, where identity controls, network boundaries, and posture validation reinforce each other. Beginners sometimes search for a single setting that guarantees safety, but real-world security is more often about building a narrow corridor where attackers struggle to move. When runtime isolation is layered and consistent, compromise becomes less scalable and less profitable for the attacker. As you connect this topic back to securing images and registries, it becomes clear that runtime isolation is the final checkpoint that limits damage even if something risky slips through earlier stages. If an image contains a vulnerable library, strong runtime controls can still reduce the chance that exploitation leads to full control of the environment. If a dependency behaves unexpectedly, constrained permissions and network boundaries can prevent that behavior from reaching sensitive resources. This does not excuse poor hygiene upstream, but it acknowledges the reality that defenses can fail and that containment matters. Runtime isolation also supports immutable patterns, because when containers are easy to replace, defenders can remove compromised instances quickly without trying to clean them perfectly. In that sense, isolation is both a protective wall and a practical tool for incident response, because it buys time and reduces uncertainty. The environment becomes easier to defend when replacement is normal and boundaries are strong. To close, isolating containers with least privilege runtime settings and strong boundary controls is about making sure containers remain what they are supposed to be: focused environments that do one job without becoming powerful general-purpose platforms. Least privilege limits what a compromised container can do inside itself and what it can reach outside itself, while boundary controls shape file system behavior, process visibility, network reachability, and resource consumption. These controls matter in cloud security because container environments are dense, fast-moving, and highly interconnected, which makes them attractive targets for attackers who want to pivot quickly. When boundaries are strong and consistent, detection becomes clearer, response becomes faster, and the blast radius of a single compromise becomes smaller and more manageable. The most valuable beginner lesson is that container security is not just about building a clean image, but also about running it in a way that keeps power tightly constrained. When you treat runtime isolation as a first-class design goal, you turn containers into a safer building block rather than a convenient risk multiplier.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.